are moving on to a talk from Microsoft Research. Let's hope it will work out.
Yeah, at least.
So meanwhile, let me present the speaker. Madanlal Musuvathi, he is from Microsoft. He's a senior researcher there. Yep. And he's going to talk about Microsoft Collective Communication Language with some interesting acronym that I cannot pronounce. So, he will figure that out.
Yeah, if my computer works. Cool. Let me promise that I was more organized, just that when we tried doing the setup, my computer crashed. So, cool. So, hi everybody. Thanks for the introduction, Mark. So, I'm Madanlal Musuvathi from Microsoft Research, and I'll be presenting my work with my colleagues on generating high-performance communication kernels with this funny name called MSCCLang. So, let me explain why we started with this acronym. So, NCCL is a communication library from NVIDIA. It stands for NVIDIA Collective Communication Language. And then we had an internal library called Microsoft Collective Communication, which we called it MSCCL. Oh, sorry. So, which is called MSCCL. And then one of my co-authors decided that MSCCLang was actually a funny enough acronym for this paper. So, we all know that ML models are increasing dramatically in size. We saw it in the keynote today. Roughly, the latest trend is that these models are growing 10x per year at an amazing rate. So what this means is that these models cannot fit in a single GPU. So invariably, both the inference as well as training computations are distributed. So as a result, ML computations are increasingly becoming communication bound. So it is important to optimize these communication kernels. So in ML workloads, communications happen through what are called collective communications, where a bunch of GPUs come together to collectively perform the same operation. So here is an example. Let's say we have 3 GPUs, each with their buffers. You might want to do what is called an all-reduce operation, where you compute the sum of all these buffers, and you want all the GPUs to have the result. A similar such operation is called all-to-all. Say you have 3 buffers that represent the 3 rows of a matrix, like a matrix sharded row-ways. And then you might want to do a transpose, so have a column-way sharding. And so you do this performance called all-to-all. And as ML computations have become more prominent, the kind of collectives that we need have become more sophisticated. So if you look at what it takes to implement these communication kernels very efficiently onto GPUs, you need broadly 2 kinds of choices. One is what I call algorithmic choices, and then implementation choices. So a communication algorithm determines how the GPUs route data among each other to implement this operation. A common example is the ring algorithm for doing the all-reduce, where the GPUs arrange themselves into a ring, and then they take turns sending their data among themselves. Tree algorithm is another one where you might care about latency, and so ring might take a tool, involve a lot of steps, so you might do a tree algorithm. And so usually when you're designing this algorithm, you care about making latency and bandwidth trade-offs. And also you want to make sure that you're using the high bandwidth links between GPUs within a node efficiently, as opposed to inter-node communication, which has relatively lower bandwidth. So once you decide on this algorithm, then you have to make lots of nitty-gritty implementation details. Things like how do you maximize the parallelism using the available SMs? How do you maximize the link utilization? And of course, you want to minimize launch and synchronization overheads. And more importantly, or equally importantly, you want to make sure that you don't introduce bugs when you're optimizing these kernels. You want to make sure you're dealing with relaxed consistencies and not introducing deadlocks and so on. So recently, there's been lots of work on how you synthesize novel algorithms for different collective communication. And the reason why you need these novel algorithms is because based on your input workload or the backend in which you're compiling, different algorithms might work better in different scenarios. So this work is more on taking an algorithm and how we can automate compiling these algorithms to attain handwritten performance. Okay. So that's what our work is doing, and part of our motivation of this work is to enable more research on people generating novel algorithms for implementing communication kernels. So a brief overview of our work. So we have a language, compiler, and a runtime. Our language is a high-level DSL that is Pythonic, so it is a valid Python program. And it's chunk-oriented. I'm sorry for the font here. So what I mean by chunk-oriented is that the program, you specify what's happening to each chunk while implementing this communication algorithm, as opposed to specifying what each thread or node does. So we believe that this is a more natural way of specifying your communication algorithm. And this is, it's a sequential program. The correctness is specified by the sequential run of this program. So if you run it, you can actually see what the collective does. You can debug it, and so on. And part of our job is to, take this compiler, take this program, and then compile it while ensuring the semantics of this program. And one thing that you could not see because of the font is that we wanted to allow users to specify optimization constructs in the language. So this is inspired by things like halide, where rather than the compiler doing all the optimizations, the compiler can actually take hints from the user on how to do those optimizations and when. So our compiler takes such a program and then generates a very efficient IR. So basic goal of the compiler is to take this chunk-oriented program and then map it onto different thread blocks across all the GPUs while performing a variety of optimizations like parallelization, tiling, scheduling, etc. And also the compiler ensures that the generated code is correct with respect to the sequential program with guarantees of no deadlocks or data races. So our IR is then interpreted by our runtime. So what we did was we embedded an efficient interpreter directly into Nickel, which is the collective communication library from Nickel, from NVIDIA. And the advantage of this design is that we can reuse all of the runtime facilities already implemented in this production library. So it supports all the different interconnects and so on. And it's also, this entire stack is API compatible with Nickel. So if you already have production workloads which are using Nickel, porting them to use MSCCL requires a few lines of change. And so that was actually a very important design decision in our work here, so that we could not only do research, but at the same time, evaluate the research on production workloads. So I will go into detail on some of the optimizations. The rest are on the paper. So one common optimization that we do is what we call chunk parallelization. So imagine that a node wants to send a chunk of data to the other node. So what you might want to do is to actually split the chunk into 3 parts and then send these 3 parts in parallel. The advantage of doing that is that you use different links for sending these, and so you can do it faster. And interestingly, what we found is that even if you're using the same link, sometimes 3 thread blocks right into the same link gives you better link utilization because of the way the transport layer is implemented in CUDA. So again, the advantage of our language is that you can specify this optimization with just a single line, as you can see here, line number 3, which tells you, take a piece of computation and just parallelize it, and then the compiler will automatically do this optimization for you. And this is heavily inspired by Halide. Another optimization is what we call chunk tiling. So again, if you're seeing the pattern, many of the optimizations that you do for compute kernels have a corresponding thing for communication kernels too. And that was one of the things that we realized when we were writing the paper, is that many of the work that is done in compute kernels, we can actually translate it into translate it for communication kernels. So here I'm showing an example of a hierarchical algorithm. So what happens in a hierarchical algorithm is that you do some computation within a node. All the GPUs within a node talk to each other. And then you have these inter-node phases where you communicate across nodes using these relatively low bandwidth links. And then you come back and then do intra-node communication. So as you can see from this picture, when you're doing inter-node communication, your inter-node links are not used, and vice versa. So what you might want to do is to essentially, again, subdivide the chunks into 4 parts, and each of the computations are now independent, so now you can tile it. And so now, as you can see, by doing so, we have increased the utilization of both inter-node communication and intra-node communication. Again, our language and runtime makes it very easy to do these kind of optimizations. So now I'll go very quickly on the results. So this chart explains the performance of MSCCL over nickel. Nickel is the baseline. So x-axis is the number of, it's the buffer size on which you're doing the all reduce, and the y-axis is the speed up that we have relative to nickel. So greater than this, this gray line means that we are outperforming nickel. So what we did was we took the ring algorithm as implemented in nickel, then we rewrote it in our DSL. The advantage of writing in our DSL is we can actually play around with different implementation choices. That was the whole point. And so what you see are 2 lines, a blue line and the orange line, for different implementation choices. And the important thing here is that by making these choices very quickly, you can come up with communication kernels that outperform nickel for different buffer sizes. So this is for a given algorithm making different implementation choices. Then we can also implement other communication algorithms. So there's an algorithm called all pairs, which is more latency optimal. And again, making different implementation choices, we can get different performance curves. So again, the point here is that no single algorithm outperforms nickel throughout, but by combining these different algorithms based on where your workload is, you can pick and choose what works for you. So that's the advantage of MSCCL. So the one thing that I'm actually really proud about is not just the experiment results, but also because of the fact that all the work that we did, writing them in our programming language was less than 30 lines of code, and many of the times we can do optimizations in less than an hour. And so this is really important because the workloads keep changing, the backends keep changing, and then we can pick and choose what works for us. So to conclude, I just presented the MSCCL language compiler and the runtime. Since our paper, we actually have embedded the interpreter in AMD, so we can support AMD as well. And our code is open source, and it actually runs many of the AI models that you know and love, like the GitHub Copilot today. Thank you.